Tell us your name and tell us about your project.
So my name is Clinton Davison. I was born October 22nd in 1881 in Bloomington, Illinois. I attended the University of Chicago and went on to receive my PhD from Princeton in 1911. I then went on to work for the Western Electric Company, which would later be known as Bell Labs, in the engineering department after World War I. My partner Lester Germer and I worked together for the Western Electric Company, and we were given the task to study the surface of a piece of nickel, but this led to what would later be known as the Davison-Germer experiment.
What were you guys trying to find?
The initial goal was simply to study the surface of a nickel, like I stated earlier. However, we ended up trying to demonstrate the wave nature of electrons and confirm de Broglie's hypothesis that electrons possess wave properties. This came about due to the fascination of de Broglie's views about particle wavelength and velocity and its relation to the project that we were already doing.
Where did the project or experiment occur?
The experiment took place in what is now known as Bell Labs, which is located in New York in the United States of America. Bell Labs is most notably a communications company, but their work also involves gaining a better understanding of science principles and exploring new scientific fields and avenues of technology.
What other significant events were going on around the world at that time?
The Treaty of Berlin had just been signed, marking the end of World War I. Also, around this time, the Communist Party of China was formed with Mao Zedong as its leader. Albert Einstein had just won his Nobel Peace Prize in physics. Babe Ruth just broke the all-time home runs record, and the Great Famine of 1921 took place in Russia. This was especially hard for Russia because of the economic hardships that followed World War I.
Who else was involved in the experiment?
The experiment was done with my partner Lester Germer and I.
What was your role in the experiment?
So Germer and I set up a vacuum apparatus used to evaluate the energy of electrons after they were reflected off the surface of nickel. The target surface we used was nickel, and we used a Faraday box to detect the electrons scattered from this surface. The Faraday boxes were mounted onto swivels so that the angles for detection could be changed. Upon these changes in angles, we noticed peak intensities, and this proved the wave behavior of electrons. And by using Bragg's law, we were able to find the lattice spacing of the nickel crystal, and this proved that electrons behave like waves as they exhibit diffraction patterns upon scattering from a surface.
What impact did your experiment have on the physics community?
It resulted in a better knowledge of the properties of electrons and allowed for further research to be done in more depth with these facts and properties in mind. It also proved the already advancing field of quantum mechanics and helped establish it as a relevant field in the physics universe and not just a theoretical application. While vacuum tubes were not readily available for most scientists until the 1960s, our experiment did allow for the use of low-energy electron diffraction, or LEED diffraction, to examine the surfaces of other crystallized elements in their respective lattice spaces. Our experiment also led to the creation of the electron microscope.
Did this experiment receive any awards or form of recognition?
This experiment did win the Nobel Peace Prize in Physics, which I share with George Paget Thomson, who independently came to the same conclusions through his own experiments at roughly the same time that I did.